instructor we have is Vince. I'll let Vince say his last name because I'm going to mispronounce it, but from DGI. And he's talking about quantitative classification techniques applied to physical rock property and lithogeochemistry data at the HudBay Lalor deposit. Vince was first introduced to borehole geophysics while attending the University of Waterloo, where he obtained an honors degree in earth sciences. He subsequently gained valuable experience working at the Geological Survey of Canada in the borehole geophysics section of the Mineral Resources Division before founding DGI Geoscience in 1997. Vince has been directly involved in over 300 projects incorporating in situ physical rock properties and/or borehole imaging for mining, mineral exploration, hydrogeology, geotechnical, and environmental applications. He is passionate about the intelligent use of technology, turning data into knowledge, and single malt scotch.
There's that little green button is a lightsaber.
Perfect, lightsaber, cool. All right, hello everyone. Thanks for the invite, and thanks for the BCGS and HudBay for putting on this great event. I'm looking forward to learning a lot from the rest of the speakers over the next 2 days. A little bit more about myself and DGI that's sort of relevant to this talk. While I was at the University of Waterloo, it was a co-op program, so one of my first jobs was for a hydrogeology consulting company, and as a student, first or second year with very little experience, I was immediately thrown on to supervising a drill rig and logging core. So fortunately it was a quaternary geology, so it wasn't too complex, but there was also another student that was logging the core on another drill rig at the same time, about a couple kilometers away, and we were comparing notes, and we were describing the same rock differently. We were constantly debating, is this a sandy silt or a silty sand, and is this greenish gray or brownish green kind of thing. Turned out that he was colorblind, so that explained why we weren't agreeing on the color, but it showed how easy it is to be inconsistent in the way we were describing the rock, regardless of how hard we tried with this descriptive subjective method. So it was on the same project that I was first introduced to borehole geophysics and physical rock property measurements. And this guy just backed up a vehicle to the borehole and lowered down this instrument, and I was like, wow, we're getting quantitative measurements. I'm seeing things in this that it's hard to actually see in the core. We're able to see finding upward sequences and coarsening upward sequences that were very apparent from hole to hole, and that really helped us match the two different classifications from the two different under green geologists, I would say. And that was very helpful to just having a consistent classification scheme across the board. So shortly after that, I moved on to Geological Survey of Canada. I saw Jonathan Monafumbo in the room, worked with him about 20 years ago. Do you believe it's been 20 years already? So I learned a lot from Jonathan and Pat Colleen in that group. Had the great opportunity to travel across the country and apply this borehole geophysics and physical rock property measurements to mineral applications across Canada. So that was great. And shortly after that, I founded DGI Geoscience, and we've been doing that ever since. So basically, my talk today is looking at quantitative classification techniques. Primarily, we started this for physical rock properties. The reason for this, I'll get into it. Maybe I'll start the talk and walk through that. Here's basically an outline of the presentation. I'll be talking about quantitative classification schemes. We'll move on to goals and objectives that were specific for work at the HudBay Lalor deposit. We'll overview the work that was completed. This is like about 5 years ago now, so I had a good chuckle going back to this data and the analytics we used 5 years ago. We've certainly progressed a bit. I thought some of our plots and our software we're using at the time was a bit primitive and archaic, but it's good to see progress over those years. And then we'll look at some results and observations, basically with rock property domains and lithogeochemistry domains, and I'll just touch on some conclusions in summary. So basically, our initial efforts were really trying to get consistent quantitative data. We're talking about a data-driven approach, and when you have a data-driven approach, you're basically relying on your data. So you better have, it's the whole garbage in, garbage out thing. So our early years on the data acquisition side was really focused around taking some instrumentation that wasn't necessarily standardized and lacking calibration standards, and really working to ensure we get consistent data so that for any given borehole across an entire project, you could return to it at any time, or map a different borehole, and if you're the same rock type, get the same measurements. So that idea of having consistent quantitative data was critical. The whole premise was to obtain richer quantitative measures and apply robust data analytics. Alan Galley talked about real-time measurements, like some of these measures we can take and basically right out of the drill hole as soon as you're on it. So there's this opportunity to extract value and information in a very quick process and dynamically integrate these results into 3D modeling. So basically, we're using a combination of data validation, machine learning, cluster analysis, and conventional statistics. That data validation portion is a very important one, and it's probably the most time-consuming. That's basically making sure that the data going into it is consistent quantitatively across the board before getting yourselves into trouble. And the two major outputs are really creating quantitative classification schemes and building proxy relationships from disparate data sets. I'm mainly going to talk about classification schemes today. So there's always challenges with the data. I've already touched on that. It was nice to read in the New York Times recently that I'm not the only one struggling with this problem. Across the board, it's basically 80% of the time is based on preparing the data prep, looking at data sets, making sure it qualifies to take a data-driven approach, and cleaning it up so you can actually extract value from it. So that's a very important piece, and not to be overlooked. So basically, here's an image that shows why we went down this path. This isn't from the Lalor deposit, but it just illustrates the reason behind this. Laser pointer, you showed me that. Oh, wrong one. Gotcha. Right here. Okay, gotcha. So here's basically the rock codes. All the green here is metabasalt, and here's a bunch of physical rock property traces. If we focus on this magnetic susceptibility, we can see that for the same rock type, we've got a non-magnetic response, a high and variable mag response, and an intermediate, more homogeneous mag response for the same rock unit. Our job for this project was to basically come up with physical rock property fingerprints for each lithotype. So it's a bit invalid to just press a button and spew out statistics. And if you look at it, we're just looking at one parameter. When you start looking at some of the other ones, here's something that there's a big change here that's not accounted for. And this is probably something that's very difficult to see visually core logging, but it is apparent in the physical rock properties. If we were to just press a button and spew out statistics, this is what we get for each rock type. This particular lithology has a high and a low gamma response. You get these bimodal, trimodal distributions. So by taking an approach where instead of forcing the physical rock properties into the same classification scheme that the geologist uses during visual core logging, we're looking at what do we have working for us. We've got massive amount of multi-parameter data that's continuously acquired down the borehole. So we can use this to our advantage, and what we've done is developed a process that very quickly and efficiently domains all this data into rock property domains. And I'm going to jump into some example. Here's basically showing the same thing in a different way. Color-coded by rock property domain, same data from core log lithology. So you can see that there is a correlation, but this would be a far better classification scheme when you're looking at what are geophysics going to show you, what are the physical rock property contrasts are going to show you from a remote sensing application. And we can also look into how do these relate to each other, the two different classification schemes. I'll skip over some of these because I don't want to go over time. So some of the specific to this HudBay project about 4 or 5 years ago, the initial goals were to take some of this historic data from a bunch of different sources and bring them into a common platform. I think GoCAD was the platform of choice, and to really look at these various inputs and break down some of those different silos and look at the geochemistry data, the geophysics, the geology, all in the same space. So our role was more of a supporting role. We were basically supporting this process through acquiring physical rock properties and interpreting them. And the process we developed to come up with quantitative classifications for the physical rock properties was also applicable to the geochemistry. So we basically did it on both data sets. Now, I'll throw out my disclaimer that I'm absolutely not a geochemist, But the process works for classifying into domains. I'm not the right person to tell you what these domains are, what the significance of these domains are, but through this process of going through this with several clients over the years, we really found the value of sitting down with, we create these domains and interactively look at them with a client, and we extract value and actually apply meaning to them. So this is basically me arm waving, saying that there's a disproportionate amount of, for all the work that occurs and the money spent on drilling, there's a very small percentage of a budget that's actually allocated to physical rock property acquisition. When you look at the oil and gas industry, 100% of every borehole is petrophysically logged, and this is a back of the envelope calculation. But a very small number of holes are actually measured in the rock property and the minerals industry, and HudBay was really forward thinking in initiating this program and trying to wrap our heads and really understand the physical rock property contrast for this deposit. So basically what was accomplished, we measured 17 strategically chosen holes, strategically chosen because they are intended to line up with sections with other geophysical surveys. And they were expected to have, the contrast and cover a representative suite of the lithologies that were logged on the site. These occurred over multiple mobilizations, so that QA, QC, and standardization was important. On one mobilization, we were called back on short notice, and the equipment we used first time was in Alaska, so we had to sub in different equipment from different manufacturers, but the data all worked out because we had a local test hole, confirmed when we showed up with another set of equipment that the data for the entire project was quantitatively consistent, and we can interpret the boreholes simultaneously. These are the parameters we measured. I won't go into them in much detail. And again, we're focusing only on the physical rock properties in this talk. I've already covered this. So let's get into some results. So basically, we did a statistical test that suggested 7 clusters were ideal for this data set. That's just a test. What we really enjoy doing is and what could be an interactive process with a client is adding more domains. If we can force this to say, I want 2 domains, and it'll give you usually felsic and mafic, or it'll give you, ore and waste. And if you add a third one, you'll get, felsic, mafic, and ore. If you add another one, an alteration halo on it pops out, and you can keep pushing this until you solve the problem you want to solve. So it's and we've created so that you can add classes very quickly. If you compare to going back and relogging the core, which could take several months, we're talking 10 to 30 seconds, and we could add another class and look at it in 3 dimensions and see how meaningful it is over space. So we've got 2 classification schemes now. We've got the original rock types that were logged by core logging, and then we've got rock property domains here. These are the 7 in this first test case. I've added a bit of a legend here just to help everyone with these rock codes and also help myself. And just some initial observations. Again, I'm not going to go into too much detail, but some interesting things. Basically, there's multiple physical rock property signatures that correlate to R1, which are mafic rocks. So what that's telling me is of everything that's logged as a mafic rock R1 code, using physical rock properties, we could subcategorize that into 4 distinct classes. Well, that's interesting because maybe we can use some of the surface and airborne geophysics to start subdividing these different classes of mafic rocks. Just out of curiosity, everyone's always interested about the sulfides. We look across and what's mapping to the sulfides most frequently. Well, this is class number 6. There are some classes that are mapping almost perfectly 1-to-1. In this case, we've got rhyolite. Basically 80% of domain 3 is mapping, so it's almost a 1-to-1 correlation. 85% of the time that we've got that class, it's mapping to rhyolite. So on and so forth. There are other interesting things. We've got domain 2 and 4 mapped to very similar rock codes, but have distinctly different rock property signatures. And when you dig into the rock properties, you can see why. One turns out to have a much higher sonic velocity versus a low sonic velocity, and a very high gamma versus a lower gamma, which to me says one is much more competent than the other, and one is more felsic than the other one. So a lot of interesting observations that we're able to make, and it's good that these classification schemes are teaching us different things. So what do these look like? I mean, I know these titles are kind of small, but basically on the bottom, we've normalized everything, all the different parameters. We've got the parameters along the bottom. This is like density, magnetic susceptibility, natural gamma, neutron, P-wave velocity, and resistivity, and I think that's S-wave velocity. So basically, we can go through each of these classes and say, well, what's different about them? How do they change? Right, so that one I told you that was, one was had a higher sonic velocity. I think it was 2 and 4. So here we've got, a high P-wave velocity and a low gamma, and then 2 more. So we're able to distinguish what's. That was for they were mapping to similar rock types. So that was one that was mapping to almost the same group of rocks, had a distinct physical rock property signature. So now the geochemistry. So 2 different data sets. What was interesting about the geochemistry is far more boreholes to work with. On the rock property side, we only had 17 boreholes to work with, but we had a much higher data density. Less parameters, but almost a continuous measurement. Every 10, 20 centimeters, we've got a number. So much higher data volume in a less number of holes. The lithogeochemistry was basically every 30 meters there was a measurement, but across many more boreholes. So you get a broader view of the entire project. I'm just going to toggle between the core log lithology and the lithogeochemistry domains. So you can see similarities, but a bit of a different shape. And again, I'm not a geochemist, so I don't want to read too much into the results, but there's certainly some interesting trends there. Same thing as I did with the rock properties. This is lithogeochem domains on one axis on this cross tabulation and all the original rock codes there. So again, a similar approach to the rock properties. We can identify what's the geochemistry telling us that's different or similar to the original rock types, and we could basically take all these different domainings and look at them in 3D very quickly. You could observe this in 3D. What are the rock properties telling us? What are the lithogeochemistry telling us? And how does that compare to the core log lithology? And you looking at all these together, I think you can get a better, more accurate model. So this is lithogeochem clusters and parallel coordinate plots. You can quickly go through and distinguish what's driving the differences between these domains. Not anything I'm going to do in great detail now because of time, but so this is what a particular borehole would look like with the 3 classification schemes together. This is the core log lithology, geochem domains, and rock property domains. So pretty good correlation in general. I can just toggle through a few of these. So very, very similar, but there are some differences. The rock properties are picking up on some things that may be difficult to see in the core log and the geochemistry. I'd caution you a little bit on the scale, and I was talking 30 meter samples for this, so if you see a bit of depth offsets, that's likely why. We've got 1 sample to cover 30 meters, and when we get into some real busy zones, we noticed that the variability of the rock was higher than the sample interval in some points. So up on the higher up, you'd have like 100 meters of homogeneous rock. You'd have multiple samples in that same rock type, and then when you get down below the hangwall footwall contact, there was the rock was changing faster than there was lithogeochem samples. So I'll wrap up here. That was just a very brief overview. I'll touch on some of the conclusions. Basically, the geochemistry and rock property domains improve deposit understanding and can provide geologists with objective interpretive tools to build rapid, accurate 3D geologic models faster. Both the geochem and rock property domains augmented traditional core logging by identifying unique signatures and highlighting zones that are often difficult to visually identify. The rock properties are the critical quantitative link between geology and geophysics and provide geological context to geophysical survey results, inversion constraints, and improved geophysical survey planning. And one of the things that we probably could have done a better job of at this, but this is one of the early stage projects where we even attempted this approach. we've learned over the years that it's critical to work with the local team. We're very proficient at quickly identifying trends and able to compare them in 3D, but when as an outsider coming into a project that we haven't spent much time, like boots on the ground, you've got these local experts, and from experience, the process, you really benefit from the process when you're interactively going over these results with the geochemist and the geologist with all the experience and the local geophysicist that has local knowledge and background. With that, I'll say thank you.
Questions?
Yes. Yes.
I have one question, one comment.
Yes.
The question is, you mentioned several rock properties. The last one you mentioned is neutron,
Yes.
but that's not a property.
Yes. Correct. Yes. Yes. Correct. Yeah.
Mass density?
We're looking at basically it's a hydrogen indicator, so you're looking more like porosity.
All right.
Yeah. Yeah. Correct. Yeah. I shouldn't have used slang. Yeah.
And I have another, it's more of a comment. You mentioned there's the missing link is rock property. I think there is a missing link in the missing link. I bet, well, everybody knows here, especially people working in IT, 10% disseminated sulfide is not equal 10% sulfide in veins. We all know that.
Mm-hmm.
But I bet 10% sulfide in veins is not equal 10% sulfides in veins. My comment is that we,
Can you hear at the back of the room? Sergio, stand up and shout out your question.
all right, 10% sulfides in veins is not equal 10% disseminated sulfides. We all know that from IT. But 10% sulfides in veins is not equal either to 10% sulfides in veins. The missing link we're missing, we're not seeing, is the orientation of the beam. You
Yes,
mentioned
yeah.
that petroleum geophysicists
Yes,
have been
yes.
working with borehole dogging for always.
Yes.
I have always been working with anisotropy for always.
Yes.
And I don't know why we mining geophysicists don't like
Yeah.
to work
I actually agree with you 100%. And if I had 40 minutes to talk, I would have thrown in a bunch of structure information, because we're also capable of measuring structure downhole and taking that into consideration. There was just no way I was going to get that in a 20-minute talk. But I agree with you 100%. Understanding the structural controls, which can also be measured at the same time as these rock properties, are very important. Yes, I agree with you 100%. Yes.
Ken, go ahead.
One of your example, you said it wasn't from Lalor, but you showed that within what appeared to be a monotonic rock, there were actually significant changes. And my anecdotal observation is if you can somehow feed that back to geologists, maybe even arm them with a susmeter, they can actually start to identify those things, but they're often bored seeing these big monotonic sequences, particularly when they're not related to mineralization. And that's one of the other things. We can detect things that are real changes in the geology, but if it's not part of your system, it's just often kind of the background chatter that you lump a rock together and say within that there are natural variations. So I would just say probably you're right. If you can link in with people on site, they see a lot of stuff that they've just dismissed or put it together and say, well, there's this rock type B. You see a lot of detail and you get excited about it, but actually it may not actually be germane to the problem.
Exactly. No, I agree with you 100%. And I also think that that was common. Like, we see that all the time, right? That wasn't an aberration. Almost every project will see distinct differences between the core log geology and the physical rock properties. And in the geologist's defense, he doesn't have that information at the time that he's core logging. And if we don't get that to him fast enough, the core is gone, and they're not going to go back and relog the core. So I think it is important to have sort of a speed component. And you have to look at this from a systematic approach that, can we get this type of information in the geologist's hands at the time that they're logging the core? And then a lot of these, disparities kind of go away earlier on, and you don't have to reconcile. But given the fact that we're also doing this with geochemistry, which takes a while, then you can still create these different domain models. But I agree.
I think at the back first, please.
Okay, I'll start with the second question first. You can measure a lot of these similar properties on core. It can be challenging and a bit more labor intensive, not with the same equipment. We're sending specialized equipment down for measuring down drill holes. You can take a lot of the same measurements on core with the understanding that the original fluid may not be in the rock. It's under a different pressure and stress condition, and it can be a bit slower. But it's quite common to take magnetic susceptibility measurements on core. It's common. You could put a spectrometer on top of the core. You got to think of the shape of the core and the geometric effects and that kind of stuff. So it's possible to take a lot of these measurements, and there are some physical rock property labs out there that do that. So you can do it after the fact. It'd just take a bit longer, and you probably get, less samples. Your first question about cost, I mean, it varies on the depth of the hole, but roughly, probably 5% of the drilling cost is sort of today's general rule of thumb.
I think we had two more questions here. Al and
Theo, or who? Yeah.
Mine was adding to Ken's over there that, that boring stuff that the geologists are finding boring, may be of critical importance to the engineers who are going to build a mine, for example, right? They may want to know where those shell patterns are, where those faults are. So geologists and the boring bits may still be very important.
I agree, and I skipped over a few slides that would basically expand on that fact. Is that when in the exploration stage, you've got an opportunity to take some measurements down the drill hole like this that can help the geologists, but at the same time, that same information can be recycled on the next stage. This has happened several times for us where it goes to feasibility. So our original reason for being there is to understand the rock properties in a geophysical context. Then the mine goes to a feasibility stage, and now we've got hard data that can help correlate to geotechnical problems. And we may log the orientation using televiewers for improve our structural geology understanding. And then it comes to a pit shell design, and we don't have to drill a whole bunch of brand new holes just to understand the geotechnical orientation for a pit shell design. There's been a number of projects where we've accelerated the program because we've already had the data and basically bypass a second round of drilling, get your results sooner, and save a lot of money. So that's there's some other points that I left out. So. Yeah.
Yeah, Vince, just to follow up on that, I mean, when you think
Stand up, maybe, so people in the back can hear.
when you think of something about what's going on in Australia right now with the exploration technology, CRC, where they're actually trying to telescope the time frame so that geologists are getting the geochemical and the rock property information on site, and so you can start making decisions in a lot smaller time frame. And I think that's going to be what we see in the future a lot more. But I guess the second question is, considering the different scales that sampling is taking place between geochemistry, geophysics, and rock properties, is it reasonable to think that we can actually develop joint inversion models with this data?
I think so. I mean, I'm not an inversion specialist, but we're acquiring. I mean, the first thing that's important is because of their continuous measurements, we're mapping the variability. So really, the question is the variability. Like, how big are these things? How rapidly is it changing? So from this style of data, that where you're continuously scanning the rock, you could basically see how quickly the physical rock properties are varying. Is it something you sort of have to homogenize because it's the variability is very high, so you've got to average a value over a large area, or is it homogeneous? We can map that through this process. So I think the fact that you're taking consistent measurements, not just a spot measurement here, and in the rock property world now, we've done all kinds of work on linking geochemistry to the rock properties, and that there's the scale issue. More often than not, we have a tighter sampling interval than this project in terms of the geochemistry. So.
all right, thank you very much.
Right, thanks.